this through a magnetic solid-state environment.
Exactly. Thank you very much. So this is work like together with Jaroslav Jakovniak and Shane Kelly. And I think it fits nicely into the conference of quantum spinoptics because it combines like elements of spintronics on the one hand and quantum optics. So because the generic setup we are looking into is the following. We have like two NV centers, or like color centers in general, which are integrated into some magnetic environment. And we already heard by Amir that like these NV centers can be nicely controlled optically and be used as really good sensors like to learn something about your environment. And here we would like to like turn things a little bit around and somehow use the environment that we can control by spintronic tools and somehow manipulate the correlations here to imprint entanglement onto the color centers. So that's the main idea, and the question is like, how can we do this? How can we entangle the color centers in such a situation? And generically, I just want to like to give you like the Hamiltonian we're thinking of. So we have some, we divide it into three parts. We have the system, we have the environment, and some coupling. So the system is simply non-interacting color centers. It's just like given like SL and SR are just, you can think of the Pauli matrices, just some spin qubits, and they're pointing in a certain direction, which is given by these vectors delta. But we're always assuming that they have like the same magnitude, so they're like degenerate. And then we have some magnetic environments. So in the very easy situation, it's just like some stiffness, so which favors the A is the magnetic stiffness, so it favors like a parallel orientation, but there can be various terms like that give rise to some interesting structure or correlations in the system. And of course, we have the coupling, and as we learned already, the coupling is of a magnetic dipole kind, and like you can write it in the following way. You basically have these spin operators of the NVs, which are dotted into the stray magnetic field, which is generated by this texture. So you have some kind of Green's function that propagates like your magnetization MR to some point at the NV center, and you feel the stray field. And like we already heard, like we have this filter function with k and e to the minus k, which says you don't couple to homogeneous magnetic fields, and all these details go into this kind of coupling. And the way how we want to describe it is in terms of master equation, and like Anna already gave a nice introduction to this. So we have the following assumptions. So it's always weak coupling. We do the usual Born-Markov approximations and integrate out the environment so that we are left with some reduced density matrix for our NV centers. And it is of the following form. So we have a time derivative of rho. And the first part here is just the usual von Neumann equation. And now the environment gives rise to two effects. On the one hand, we have this delta H. Those are also known as like lamp shifts in optics. And we have this dissipation part. This W is like a super operator. It describes all kinds of dissipations. I will go into detail later. And now the question is, can we use these new terms which are generated here in this equation to imprint some entanglement? And maybe the first thought is, of course, you have to use the coherent dynamics to somehow imprint some interesting entanglement, so this lamp shift. And in particular, like non-local terms would be interesting. And this is basically now like the counterpart to what we just saw in the last talk. If we now look at what the renormalization actually is that is going to be imprinted onto this color center, it can be of the form like the first part, which is something like RKKY, but there can also be some DMI interaction if there's an inversion symmetry breaking in your environment. And these non-local interactions have like potential to create some entanglement. And importantly, these parameters now are of course given by some, in the example we saw before, it's like the real part of the Green functions of the environment. So it has some information about the fluctuations, and it's like of the form m, like mi, mj at different positions and different times. Okay, this is one possible source, and we also learned that, of course, you can also use the dissipative part. It's like we have some absorption, emission, decoherence, all is included in this, and also there we have non-local contributions. So we can have all these collective emission and absorption phenomena that were already discussed in previous talks in the context of superradiance and subradiance. This is yet another possible source to basically engineer some or create some entanglement in your system. And importantly, like here it's not the real parts of the Green's function that entered, but it's more like the lesser and larger Green's function in the context of like the solid state language, because these are actually dependent on the population somehow. Like it's not only the spectral properties that are important, but also the population. And this can be used now because we don't have now a vacuum state that we're coupling to, but some real solid state environment where we can tune populations and with more angles somehow to go to a real non-equilibrium situation. Okay, so that's another source of the entanglement. And like in a recent publication by G, a former grad student in Jaroslav's group, they nicely showed that it's like indeed possible to create some transient entanglement with these germs that are generated. However, we're interested, can we also get something in the steady state? And so what do we have to do? First, generically, if we take our environment and just put it in some thermal state, irregardless of what the Hamiltonian looks like, it can be very correlated. In a weak coupling limit, any properly like derived master equation will eventually lead the system into the Gibbs state of the system Hamiltonian. So the only information that we get from the environment is the temperature, and the Hamiltonian is still the same, so there's no correlations if they are not originally interacting. So there's no chance. So just a Gibbs state is just imprinted onto our color centers. So one message is already we necessarily have to go out of equilibrium in order to get some steady state entanglement. So we drive the system, and one natural strategy is just, okay, let's assume we have some kind of spin accumulation. We basically pump now our system with some spin. Spin is overall conserved, so we have a symmetry where like we have this small SZ, which is the spin of the NV centers, and the large SZ, which is the spin of the environment. And all the Hamiltonians, like the system, the environment, and the coupling, they respect this conservation. However, then you can also show that if you start in such a generalized Gibbs state, so you have now some spin accumulation, and this is nicely shown in this paper by Gano Challa, that in the steady state, there's again going to be some generalized Gibbs state imprinted. So now you only have two informations of your environment, namely the temperature and the spin accumulation, and it's still completely uncorrelated. So that's also not sufficient, because even for conserved quantities that are pumped in my environment, you're going to imprint a like generic generalized Gibbs state.
Can I ask you something?
Sure.
Don't you have the dipolar interactions that you use to couple them, don't they break?
Right, that's the point, yeah. So because the coupling doesn't just, in general, like you can assume, like for example, exchange coupling or something that would still respect the symmetry. But now an important ingredient somehow to generate the entanglement is actually that we break somehow the symmetry. So we still, like one strategy that we follow is, okay, now we pump our system and we still retain these local symmetries. So spin is still a good quantum number in both the environment and the system. But we break the global symmetry because this coupling somehow scrambles this spin conservation. Like you said, in dipole coupling, the dipole-dipole coupling is a natural candidate that does it like already in our system. So in such a situation, it's really not clear what the steady state is. Maybe we can use some hidden time reversal symmetries to figure something out about the state. But in principle, there's at least the chance to create some entanglement via spin accumulation. And this is basically one strategy we followed, but I'm not going to talk about that. This is part of the poster by Vinsu, so it's some little advertisement. We took another strategy, which is basically we're going to a very like non-equilibrium situation, and it's basically the system that we learned already about from learned something about from Rambert. It's this pair creation, Magnon anti-Magnon pair creation system. So it's motivated somehow by like or in the context of all this Hawking radiation, which corresponds to like this interesting physics where you have like you're at the edge between general relativity and quantum fields. So you have at the event horizon of your black hole some pair fluctuations where one photon goes into the black hole and the other one is emitted as Hawking radiation. So this physics is actually kind of similar to the ones I'm going to introduce in the following. However, I'm not an expert on this Hawking radiation, but I've read that under optimal situations, the temperature that you can measure from this Hawking radiation is of the order of like 60 nanokelvin or something. So it's like impossible to measure. However, in the 70s or 80s, William Unruh came up with the idea that you can also like somehow find this Hawking physics in analog systems. And in particular, he was thinking about like having some fluid and boosting this fluid to supersonic speed. So, and if you do this, and you are on the left region here, so you're now supersonic, then any phonon that is created in this region can only travel downstream. There's no way that it can escape in the other direction. So in a sense, at the interface to the subsonic region, it seems like there's some kind of acoustic horizon. And you get similar physics where you also, in the quantum limit, get some pair creation. And a key ingredient to do this, to boost your fluid, is actually the physics of instabilities. So what they're doing is, here I took some examples from the superfluid. If you want to boost the superfluid, which basically corresponds to like winding up your U1 order parameter more and more, you're going to tilt your dispersion until here on this side it dips into the negative energy region. So there's some instability going on, and at the interface something interesting happens because positive and negative energy, they simply couple. Okay, and there's a nice book about this analog gravity phenomenology, and in particular the chapter 9 discusses in detail how you can like deal with the pair creation of this situation. And of course, one natural question is, can you do something, find some analog systems for magnetic situations? And there was, I think, Rambert, the first who came up with this magnonic black hole idea in 2017, which is basically, as I understand, is like a straightforward analogy of the superfluid discussion, where you have also some linear dispersion in an easy axis, in an easy plane ferromagnet, and by using some spin transfer torque, they also are able to basically tilt your dispersion relation so much that you have some instability. And however, we are more interested in another system which was introduced in the last talk, in the spirit of this bosonic Klein paradox. So it's the following: we have like on the left-hand side a magnet, a ferromagnet, which is in the ground state, so it's pointing with this magnetic field. And on the right-hand side, we have the magnetization opposed, the anti-aligned with the magnetic field, so there's some instability. And like we already learned, we have to stabilize it. And this is a very interesting system to couple to the NV centers here. So we constantly have at the interface, due to this parametric coupling, some pair creation. And these pairs we want now to couple to the NV centers, which are like at a certain distance from the interface. And this should somehow create entanglement.
Is this a SPICE state, the one that you are?
It's like a two-mode squeeze state, or like multi-modes because it's several energies. But you can, in a sense, think about it like this. Yeah. Right. So I would like to go a little bit more into detail about this system. So on the left-hand side, the magnetic field is pointed along the magnetization direction. So it basically shifts your parabola of your Magnon dispersion up. And you can find then like this usual Heisenberg equation here for this psi L operator, which is simply like some lowering, like some annihilation operator of your Magnons, and it's given by mx minusimy. And the Magnons on the left-hand side carry a certain spin, it's plus h bar. On the right-hand side, however, the magnetization leads to this instability, so you can think of the parabola like being pulled downwards, and also the Magnons always carry the spin minus h bar. And right. So what happens now if we couple the left and the right? Oh, sorry. First of all, of course, this gives rise to an instability because in principle, now we can just excite negative energy Magnons, which eventually leads to this inversion of the magnet, and we have to somehow stabilize it. And Rembert already said how to circumvent this, and the idea is that we basically have to overcome the Gilbert damping, because the Gilbert damping is usually proportional to the frequency, and when the frequency becomes negative, it is not a decaying solution anymore, but like a exponentially growing solution. And to somehow always have the right sign that everything is always nicely decaying, you can introduce some spin source or like some spin torque, and this drive is able to stabilize everything. And this is just the condition. So this drive has to be larger than the alpha, which is like this Gilbert damping coefficient, times the HR, which is like the most negative energy that is possible here at the bottom.
I'm not familiar with Gilbert physics. So you are having this dynamical instability, so there would be some growth, and then you are tapping down with Gilbert damping?
So the Gilbert damping usually leads to a decay of the Magnons.
Right.
However, it is proportional to the frequency. So here you have negative frequencies, so it changes the sign, so it leads to some growing solution. And we don't want these growing solutions because it's an instability.
Yes.
So we somehow have an additional term, which is like some spin torques or some spin current that can be injected into the system or like removed. And this stabilizes or gets the sign again right of this.
I agree, but the steady state is in this case what?
Sorry, what?
After you cure the instability, you will reach some steady state because of the spin torque term, right?
Yeah.
Which is the steady state that you reach? It's still a state with some squeezing, with some correlations between these.
Right, I will come to the steady state, yes.
Because this was your problem at the beginning, right?
Right, yeah, this is...
We're trying to give solutions.
I'm now basically deriving how we come to this steady state. Like it is of the squeezed kind, yeah. Okay, so like what happens if we couple them at the interface? The coupling is of the sort that we actually couple like psi dagger left and psi dagger R. So like I said, it's like this kind of parametric coupling, and you always couple positive energies on the left side with negative energies on the right-hand side. And this is the main mechanism that is basically responsible for this pair creation. And but it's kind of unnice that we always have to couple like positive and negative energies. So that's why the idea of antimagnons is useful. And the idea is just that we now basically double the degrees of freedom. We flip the dispersion. We not only have the parabola upwards, but also downwards. And then we just consider only positive energies. And we see that the coupling to the negative energies now are just like couplings of magnons on the left-hand side with antimagnons on the right-hand side. And the way we actually solve the problem is just making some Bogoliubov ansatz. So there's some annihilation operator here, some creation operator there. They oscillate with the minus and plus I epsilon t. And then we can basically derive some kind of Hamiltonian-like equation. However, as Benedetta also pointed out, that you always have like some pseudo-Hermitian for bosonic systems, you always have pseudo-Hermitian Hamiltonians, right? Okay, so it's only 5 minutes. I think it works out. So now we can construct the scattering states. The scattering states are, so we have something interesting only happens here in this purple window, because that's the only situation where like basically red states and blue states like couple to each other. And so, and at a certain energy, we always have like 6 possible modes that are have to be considered, and we want to construct the in-scattering state. So something is coming either in from the left or from the right-hand side, and then you just look at what can be reflected. So for example, this mode is the incoming mode here. It can be reflected into this mode, or since the coupling is such that you always couple magnons and antimagnons together, you're going to be transmitted into the red mode here, which is this guy, because the relevant is always like the group velocity. So this is actually like, the ideas here are very similar to what is used for superconductors in the Bogoliubov-de Gennes formalism. And now you can also construct the second scattering state, which is coming in from the right. So we have some antimagnon coming in. It can be reflected into the other antimagnon, or it can be transmitted into a magnon on the left-hand side. And there's a third scattering state, which is not really like that important for the story, but you can come in as a magnon from the right, but there's no antimagnons on the left-hand side, so there's just some exponential decay, some evanescent mode. And now we look for all the solutions for all the energies and basically sum them up, and we have the solution for our field operator, which describes the magnons on the left or on the right-hand side. And this is now basically the solution for the magnetic environment, and we can take it as an input to calculate the dynamics of the NV centers, which we're interested in. Okay, but before I go to the NV centers, I would like quickly want to mention that like the fact that the second scattering state where an antimagnon was coming in is somehow special, because it actually corresponds to a negative energy magnon. So it behaves like, if you do the calculation, it turns out that it behaves like a creation operator. So these antimagnons actually have like commutation relations which are -1, so there are no bosons. So it's not, this whole particle-Hall transformation works very well for fermions because it's canonical, but here you have this minus sign, so the interpretation of some bosonic particles for these antimagnons is not possible. But it's still a very useful concept in this scattering formulation. And in particular, if you now relate in and out scattering states to each other, you also see that the scattering matrix now must preserve these kind of commutation relations in the sense that it is not unitary, but preserves the sigma, and the sigma just has the information of whether it's like commutating to 1 or -1. So it's 1, -1, 1, a diagonal matrix. Okay. And actually from this you can already directly see that r square minus t square is equal to 1, which is like the main ingredient for this bosonic Klein paradox, where you have the enhancement of the spin current that is incoming and it's reflected with a much larger amplitude. Okay, but even if we don't send anything into to the interface, even in the vacuum state, if we say, like we formulate now the vacuum state, meaning there are no in-scattering states to begin with, even then the fluctuations lead to this pair creation at the interface, and this manifests itself as a quantum spin current that is absent in any classical system. And if you do the calculations by basically using this field operator we derived before, and just looking at like the usual equation, which is like similar to this probability current for the Schrödinger equation, you can derive the following expression that there's always like a spin current flowing in the negative direction, and it's simply given by the transmission function. And the transmission function is integrated over this window from h left to hr. Here I simply plot the spin current as per energy as a function of energy, and there's only a contribution in this window where like magnons and antimagnons talk to each other. And if you now increase the coupling constant at the interface, so at the interface we are always like thinking about some exchange coupling between the layers. If we make the coupling larger and larger, the emission or the spin current becomes larger as well. Okay, and now we want to couple this to NVs. And before we include the Hawking radiation, I would like to mention that it's already interesting to just couple an NV center to this inverted region, because it's like basically leads already to an inversion of your NV center. It's always possible to emit a magnon with negative energy, which effectively leads you in the steady state to the following ground state. So you're in the ground state on the left-hand side, but in the excited state on the right-hand side. So here you can always, if you're here, you can always emit a positive magnon on the left-hand side. If you're in the ground state, you can always emit a negative energy magnon into the inverted magnet. So that's already kind of weird. But now, if we include this pair creation, we somehow think that, or the idea is that if the absorption and emission on left and right-hand side are approximately equal, you can create some nice singlet state where the absorption of the magnon triggers the excitation here, and the absorption of the negative energy magnon triggers the excitation from the excited to the ground state, because it's always reversed. And now let me show you the results. At first, we did some naive exchange coupling. So we said that the NV centers just couple locally to the magnetization on the left and to the right-hand side without taking this magnetic dipole interaction into account. And in fact, there are some very interesting resonances that you can see. So here I plotted the concurrence as a measure of the entropy, and as a measure of the entanglement. And on the x-axis, it's the energy of the NV centers, and on the y-axis, it's the position symmetrically around the interface. And we see that there are like certain resonances where the entanglement is quite large, and in particular at these red spots goes almost to 1. And this spatial structure has basically to do with the form of the scattering states, because there's always like something incoming and reflecting. There's some interference patterns that are already there in the field operator. And here I show some like cross sections. I think one for 0 distance and one like somewhere in the middle. And the coupling. This should be an X. The coupling is already tuned to some sweet spot at the interface, because as we've seen before, the larger the coupling at the interface, the more magnons are going to be emitted. But that doesn't mean that this is like better to create entanglement the larger this the spin current is that is going to be generated. In fact, there's some sweet spot where these resonances become like kind of big. And this can be seen even better if we use the realistic coupling to the NV centers, which is how much time?
0.
0. Oh, it's okay.
Minus 2.
Okay, so in fact, for the realistic coupling, everything is much nicer, because we already heard by the talk by Aurora that there's some kind of chirality if you have this dipole coupling to the NV centers. And in fact, you can tune it in such a way that the left NV center only couples to left moving modes, and the right NV center couples only to right moving modes. So there's some chirality here. And then all these kinds of interference patterns and this intricate spatial resolution completely disappears if we take the now more realistic situation. And we vary now again the energy and the coupling strength. And here you nicely see that there is some sweet spot of the coupling at the interface where like you can perfectly create like belt states. I also show here the cross sections. So for a very small coupling, you get in the whole like energy window like a rather small concurrence. And the larger you tune it, the closer you get to 1, but also the narrower is like somehow the resonance. So it becomes more and more unlikely to really tune to this point to create, via the dissipative coupling, your belt state. Okay, sorry for the longer time. So this is my conclusion. First of all, in the first part, I showed that a necessary ingredient is to go out of equilibrium in order to create entanglement. And in the second part, I showed that if you use like the dissipative coupling to this interesting system where you have like magnon-antimagnon pair creation, you can indeed like imprint some belt states onto your NV centers. Yep. Thank you very much.